Hello everyone, this is Meher Baba. I am currently doing my BTech second year in School of Computer Science Engineering at VIT Chennai. Today I am going to discuss you about Nand2tetris Project 3. The clock. Generally the clock is implemented by counters and which goes up for a certain value and later it resets back to 0. And here the output of the counter is connected to the input of the clock so that we can get the clock signal. And here the clock is an essential component in digital systems as it makes other systems and components to work synchronously without any overlapping. Combinational logic versus sequential logic. Here in combinational logic, we can observe that the output depends on the corresponding input value, but not on the past input value. As we seen in the diagram, here at a certain interval 1, the corresponding input value is A and the output will be f of A, but not our f of B or f of C. And in a certain interval 2, the input value is B and corresponding output will be f of B, but not f of A. Like that, the combinational logic works. And generally, the combinational circuits are built by using basic gates like OR, AND, NOT, and their combinations. And next, we can go to sequential logic. Generally, the sequential logic is not like combinational logic. Here in sequential logic, the output depends on the past input values. If the past input value is A and later on the output will be the f of A in next time interval. Generally, these circuits use memory elements, typically like flip-flops, to store the previous input values. Generally, the sequential logics can be used to build memory elements or storage devices. Generally, the D flip-flop has two inputs and two outputs. One of the input is D, which loads the data, and another input is CLK, which synchronizes the data. And it has two outputs, Q and Q0. And when the clock signal is high, the data is transferred to Q. And when the clock is low, the D input is ignored and the Q output remains same. 1-bit register and its intended functionality. Generally, a 1-bit register is a register which stores a single bit of data, that is either 0 or 1. The intended functionality discusses its allowance of storage and retrieval of that single bit of data. Generally, a 1-bit register typically consists of a flip-flop which can be implemented using transistors. And the main application of this 1-bit register is by combining a set of multiple 1-bit registers, we are able to store a multiple bits of data and we can execute a complex logical instructions also by using this combination of 1-bit registers. Implementation of the 1-bit register. Generally, a 1-bit register is implemented by D flip-flops. In this circuit, when the D flip-flop is triggered by clock signal to update its output. So, when the clock signal transitions from low to high, the FF captures the D and holds it till the next clock edge. And also, the circuit may use additional circuitry such as pull-ups and pull-downs to ensure proper operations and avoid the noise and oscillations which are disturbances. RAM. It stands for Random Access Memory. It generally provides the temporary storage space to store data and instructions. Generally from the RAM, we can get the data as quickly as we can. So we can store the data in RAM. But it is volatile in nature. Means when the power off condition in computer, we are unable to access the data which are stored in the RAMs, which is known as volatile nature. Generally, the RAM units are measured in bytes. They may vary from few gigabytes to several terabytes. Generally, if the speed of the RAM is more, then we can say the performance of the system is more, or else the performance is low. RAM abstraction. It generally refers to hiding of details of the physical RAM from software programs and presenting a virtual memory space instead of it. The abstraction allows these software programs to access the more memory than normal condition by utilizing the combination of RAM and secondary storage spaces. Generally, the operating system manages this condition by allocating and deallocating the memory as needed and swapping the data between RAM and secondary storage devices. Generally, it allows the program to use more memory than normal. But there is a disadvantage in this condition. The performance of the system is completely slower than RAM. Coming to counters. Counters are the widest applications of the flip-flops. In counters, the output contains the predefined state in the clock pulse applications. Generally, the counters used in many fields. The first field is computer programming. In computer programming, it is used to calculate the number of times a particular event occurs or a loop iterates. And second one, in digital electronics, a counter is used to calculate number of input pulses it received or produced, and it may be used in many applications. Counter abstraction. It generally refers to the process of simplifying the implementation and mainly focuses on functionality and behavior. Generally, here in counter abstraction, we are hiding the implementation process and focusing on the input and output behavior. Generally, these counters are widely used in frequency dividers, event counters, and timing generators. And counter is a sequential circuit which generates a series of output. This is the output simulation screenshots of bit clocked. This is the interactive simulation screenshot and this is the script based simulation screenshot. Now let's go through the simulation details in hardware simulator. So let's go through the hardware simulation. Get the simulator in tools section. This is the hardware simulator. So load the chip. This is in already it is there in third project A section. So load bit chip, change the input values, load value. So run by clicking on this tick-tock clock. We are getting output 1 after 1 clock cycle. So go through script based simulation and run the script. We can run as fast as possible by changing speed from slow to fast. So we can observe after 107 clock cycles we are getting output. So this is the output table for bit clocked chip. Let's load another chip, load RAM 8 chip and change the input values. Keep load as 0 and click on this tick tock clock. So we are not identifying any change in the output. So load the script. Just run the script. We are getting output after 46 clock cycles. Let's check with the output table. This is the output table of RAM 8 clocked chip. Let's load another chip, register chip, change the input value and load value. Run by clicking on the clock. Again we are identifying output after 1 clock cycle. Load the script and run the script. So we can get the output table after 74 clock cycles. Let's see this output table. This is the output table of register clocked. Let's load another chip. We can go through project B, 3B. So in projects, third project this is, and section B. Let's load RAM 4K chip. Change the input value, and as it is address section, and these are the values of the address, and these are the data stored in the corresponding addresses. So let's enter some addresses, and we can give minus values also. So type the address of any address. Suppose we are entering the address of 5 and running on this clock. So we are getting the output minus 198, which is the data stored in this corresponding address 5. So like that we are getting the output after any clock cycles. We are getting the same output. So let's go through script based simulation of this RAM 4K. So this is the script. Run the script. I guess we will get the output after 81 clock cycles. So let's check with the output after 81. Yeah, check the output table. This is the output table of the RAM 4K clock chip. Let's go through another chip, RAM 5 and 2. Change the input values, load value, and again enter some addresses here. So enter the address of 3, enter. So click on this clock. As the value in the 3 before was 0, so we are displaying the output as 0 here. So if we run further, the output will be same. Let's go through script based simulation and run the script. I guess same we will get the output after 81 clock cycles. So after completion of the 81 clock cycles, let's go through the output table. So check with the output table. So this is the final output table of the RAM 5 and 2 session. Load chip. So with this we will end up the simulation session, and we can go through all the screenshots of the chips given in this script, and let's move on to conclusion session after that. These are the simulation results of the register clocked. This is the interactive simulation result, and this is the script based simulation result of register. And this is the interactive simulation result of RAM 8, and this is the script based simulation of that. This is the desired output table, and these are the outputs of the PC clocked. These are outputs of the RAM 64, outputs of RAM 4K clocked, outputs of RAM 16K clocked, output of RAM 5 and 2 clocked, which these are discussed in the hardware simulation section. We saw these all simulations. Conclusion: through this project, we are able to build a functional ALU by using a basic logic gates, which we discussed in project 1 and 2. So by this project 3, I have gained a deep understanding in computer architecture and digital circuit and design. I hope this video a bit informative and it will be useful. Thank you.